Let's compare the mapping capabilities between the iPhone 14 Pro and the new iPhone 15 Pro. We'll be testing both the camera and LiDAR sensors on both smart devices and to see how capable these two phones are for surveying and mapping. See that the GNSS accuracy is pretty similar. We're getting 15 feet in the horizontal and 11 feet in the vertical. So that's about 3 to 5 meters, which is what you expect with a single solution GNSS observation. Now I want to test the LiDAR range on both of these phones. Some people claim that the new 15 Pro has an enhanced LiDAR sensor, so let's put that to the test. I've set up my tape measure all the way down my driveway, and I'll start by standing just 5 feet from my garage. So we're gonna start collecting data here and see if the LiDAR sensor picks it up. And as expected, at 5 feet, I can clearly see my garage. Both LiDAR sensors on both phones, they're working just fine. And for my metric users, 5 feet is about 1.5 meters. Now I'm gonna stand at 15 feet, which is about 4.5 meters, and see if the LiDAR sensor picks up on both phones. Okay, and we'll start collecting data. Yep, it looks like both phones are collecting data. It does seem like the 15 Pro is capturing just a little bit more data on the top. I do see that the left side of the garage on both of them though is not capturing data, so that's pretty interesting. But you could see a fuller point cloud from the 15 Pro at the top of my garage. And after looking at this closer, it does look like the LiDAR sensor on the 15 Pro is just a little bit more dense. I did make sure that the settings are set the same on both phones. As you can see here, all of the settings are the same. These are mainly the camera settings, but yeah, I mean, I'm keeping everything the same on both phones. It just appears from first glance that the 15 Pro has a denser point cloud. So that's pretty interesting. We're actually capturing more data, not necessarily in a longer range, but more light pulses are being emitted from the LiDAR sensor on the 15 Pro than the 14 Pro. Let's try this one more time at 25 feet, which is about 7.5 meters away from our object. Okay, and we'll start collecting data. And yeah, I am not capturing any data from either phone, which means that we are out of range for the LiDAR sensor. I'm gonna start walking towards the garage, see which phone picks up on the garage first. Here we go, we are walking towards the garage. They're both creeping up, and it looks like they both pick up at the same time. Yep, and that was at the 15-foot mark. So I can comfortably say that both LiDAR sensors on the 15 Pro and the 14 Pro have a 4.5 to 5 meter range. The iPhone 15 Pro has a denser point cloud when using the LiDAR sensor in comparison to the 14 Pro. Next, I want to see how well the SLAM algorithm for Pix4D Catch works using both of these phones' sensors. The idea here is that I'm going to start on this side of my house where this white fence is. I will then walk around my house, and the trajectories around the house should land us right back to that fence. Now, there may be some drift involved, and therefore the fence will be offset once I get to the other side, and that's what I want to see. Do both phones have the same issue, or is there an enhancement with the 15 Pro? Okay, and we're going to start collecting data. Now, I've turned off the LiDAR point cloud in the live view. I only want to look at the trajectory, which is the purple dots that you see. So I'm going to scan around the house. I'm actually going to go inside here, where I think GNSS may suffer a little because there's a little canopy right in front of my door. Trajectories look pretty similar on both devices, so that's good. Walking into my backyard, I'm going to the back of the house. And we'll finish off here in the back, right where the fence is. And looking at the LiDAR point cloud that was generated of my house, on the 14 Pro, we can see the separation between the fence. And again, this looks like two different fences. It's actually just one fence. And on the 15 Pro, yeah, same ordeal here. Looks like a similar separation. I'm gonna run this test a few times just to see the result. I've posted them right here so you can see the distances between the fences from the start till the end. And from what I can tell just by looking at this first experiment, it doesn't look like that there is any significant improvement. Both the 14 Pro and the 15 Pro perform the same when it comes to drifting, especially when you're going around an object and doing SLAM. The best way to solve this problem is to stabilize your data collection options. So I've used a gimbal before when doing this and have improved the accuracy tremendously. Additionally, using control points on the building to tie in your data sets so that you can do an adjustment afterwards. Plus, you can georeference your point cloud to a coordinate system. So last year when we were comparing the iPhone 14 Pro to the 13 Pro, I scanned this little playground structure to see how much detail the 14 and 13 Pro could pick up using the camera and LiDAR sensor. I also set a couple of targets and took positions using my surveying total station to get coordinates in order to compare the accuracies of the 13 and 14 Pro. I'm gonna do the exact same thing now with the 14 and 15 Pro on the same playground structure. Okay, I've got Pix4D Catch running on both phones, and I'm going to start collecting data. All right, here we go. And I'm getting the structure. I'm going to come over here, trying to get top and bottom as much as I can. We see the trajectories are matching on both the 14 and 15 Pro. Coming around till the end, and we're going to stop. Very nice. Let's take a look at both point clouds. Now, if we look here, we can see the LiDAR point cloud for both the 15 and 14 Pro. Now, in order to generate the photogrammetric point cloud from the camera sensor, I'm going to need to run the data sets through Pix4D. So let's head inside and take a look at these data sets and see our results.
All right, let's take a look at this data on Pix4D. So when taking a look at the iPhone 14 Pro, we can see error levels between 1 and 3 feet in the X, 10 and 12 feet in the Y, and the elevation has a consistent 3.5 foot error in comparison to the coordinates that we captured with the total station. Over at the iPhone 15 Pro, we don't see much better results. 3.5 to 5 feet in the X, a crazy 3 to 13 feet in the Y, but also we do have a consistent 11.5 feet in the elevation. And that tells us that the starting point between both of the iPhones is completely different every time, which is why we see crazy absolute errors like this. But it does suggest that there might be some relative accuracy to use, and later on in this video we do a different test to see that relative accuracy, so make sure you stick around for that. All right, back out into the field.
Now, in the last video, I set a bunch of these LiDAR target points along a 100-foot line, and I shot in the coordinates for these points using a surveying total station. I'm curious to see how accurate the iPhone's LiDAR and camera sensors are when it comes to mapping a linear line. How much drift can we expect, and is the 15 Pro comparable to the 14 Pro? And we're going to start collecting data. GPS accuracy is the same between both. Okay, we'll stop there and let's upload these data sets. Okay, once those data sets are uploaded, then we can assess the relative and absolute accuracies of the LiDAR sensor and the camera sensor. The relative accuracy will see the accuracy of the point cloud to itself. If on the point cloud I measure between 2 points and I get 1 meter, and in the real world I measure and I get 1.1 meters, then we have a relative error of 0.1 meters. Absolute accuracy will check the coordinates of all of the points in comparison to what I captured with the total station. The XYZ differences between all of the points will be used to calculate the root mean square error to give us our absolute accuracy. All right, let's head inside and take a look at this data set in Pix4D Cloud.
Welcome back to the office. Let's go ahead and use Pix4D Cloud in order to assess the linear accuracy test between the iPhone 14 and 15 Pro. Okay, here in Pix4D Cloud, I've got both the iPhone 14 Pro and 15 Pro. 14 Pro is right here on the right and 15 is on the left. Starting with the 15 Pro, I am going to inspect all of these chevron targets. And if I look at the images, I can see I am right at that corner of the chevron tape marker. So I can go ahead and save this point, come up to the next one, inspect. Okay, good. I will save. Next one. You can even make this a big image and really check and make sure you're getting that corner. So in the imagery, that looks good. I'm gonna save it. Okay, next point. A little more to the right. Okay, that might be good. Let's just check some more images. Oh, I want to go down. Yeah, that's definitely better. Okay, save. Okay, good. Save. Hey, look, it's my foot. I did go over a little bit too much. Just go down a bit. Yeah, that's better. Okay, save right there. Save. Okay, that looks good. Save. Close here. I think that's it right there. Save. And one more point. Yeah, I'll buy that. Save. Okay, that was for the 15 Pro. Let's go ahead and do the 14 Pro. Here we go. This is the 14 Pro data set. Okay, there we go. We've got all of the markers for the 14 Pro as well. I'm going to download these as a CSV. And let me go back to the 15 Pro and download these as a CSV. Okay, perfect. Here are both CSV files. Now I've got Civil 3D pulled up here, and these points that you see are the ones measured with the total station. I'm going to import points select both the points from the 14 Pro and the 15 Pro. Now these are points projected in WGS 84, so I've got longitude and latitude, and I've converted all of the elevations over to orthometric height in units of feet. And we'll go ahead and say okay. Now everything in red is the reference points that are from the total station, magenta is iPhone 14, and white is iPhone 15. It definitely looks like 15 in terms of absolute accuracy with X and Y is closer than that of the iPhone 14 Pro, and it looks pretty consistent. It looks like a drift in error. However, when looking at the elevations, the iPhone 14 Pro has the 15 Pro beat by about 2 feet. Again, both of them are about 4 to 5 feet in this instance, which tells me that the origin point is just completely off. What I'm more concerned with is the relative distance error between these points. So what I'll do is I'll export all of this data. Okay, so after compiling all of the data, here's what we have. I've got the coordinates of the total station here for all 11 points. And you can see on the iPhone 14 and 15 Pro datasets, I've reprojected everything to be in NAD 83 Michigan South in international feet. This is also the orthometric height, not the ellipsoid height for the elevation. But don't worry, when I show the results, I will also give a metric conversion for all of my international viewers. Now let's start by taking a look at the absolute accuracy. What I started by doing is taking the coordinates of the total station and subtracting it with the iPhone 14 Pro, and I did the same over here with the iPhone 15 Pro. For every point, we did this for X, Y, and Z, and to calculate the root mean square error, I squared all 3 of the numbers and then took the square root. Now when we look at the absolute accuracy, you can see in the iPhone 14 Pro there's actually an improvement with the X and Y coordinates, starting at 1.25 feet and going all the way down to 1500th, and 3.7 feet and going down to 2.9 feet. The elevation stays pretty consistent, although there is slight improvement here, and we do see an overall improvement for the RMSE for the iPhone 14 Pro. With the 15 Pro, we do have smaller errors, however we don't see an improvement. This is odd because we did have an improvement over time with the iPhone 15 Pro, but this time it looks like it actually got worse as we scan. So something for me to keep researching and to see what is happening here, but the errors were much less here in the iPhone 15 Pro than the iPhone 14 Pro. And this is also apparent here in the Y direction, although it is increasing in error as we keep moving along the path. As mentioned before, with the iPhone 15 Pro, we have about 2 extra feet of error in comparison to the 14 Pro, which is why our RMSEs are much higher with the iPhone 15 Pro than the 14 Pro. Now, this is the absolute error, which is not something that we really should look too closely at. Let's take a closer look, though, at the relative error between the 14 and 15 Pro. Down here, I have the distances between each of the points. So here, between points 1 and 2, this is the difference in X for all of the different points. I did it also for Y and for Z, and then I just calculated the slope distance for all of the points. I also did this between points 0 and 10, so I have an overall, and you can see the overall distance came out to 99.5 feet, which is pretty close to 100. So that is the measurements that we took with the total station. Over on the iPhone 14 Pro, you can see I did the exact same thing. Now these are actually related to the points for the iPhone, so I still haven't compared anything, but just at first glance, you can see these numbers are similar, which tells us that we're in the ballpark in terms of the relative distances. Overall, the iPhone 14 Pro calculated at 100.6 feet, which is about 1 foot of error between these two datasets. iPhone 15 Pro, same concept here. We went back and forth and calculated all the relative distances, and we came up with 99.32 feet for the overall, so slightly shorter than our reference data set here, but much closer than the iPhone 14 Pro. So that's pretty cool. Next, I calculated the differences between all of the distances, and as you can see here, between each of these points, we are within just a few tenths with the iPhone 14 Pro. Some spots are 2/10, other spots are 1/10, some spots are in the hundredths of a foot, so that's pretty nice. And the overall relative error is 1.16 feet. In centimeters, that is 35 centimeters, and then everything is within 1 to 6 centimeters of error. Over on the 15 Pro, we don't even exceed 1/10 of a foot in relative error. So everything was under 3 centimeters of relative error, and the overall error was 16 hundredths of a foot, which is just under 5 centimeters. So that is pretty impressive. And I created this graph to help visualize the errors. So on the left side here, we have feet, on the right side, we have meters, and this red line is the total station, purple is 14, and gray is 15. It definitely looks like the 15 Pro mimics the total station errors much closer than the 14 Pro, which tells us that the relative error of the 15 Pro is much less than the 14 Pro, but the absolute error continues to be pretty substantial as we've seen with the previous tests. That's because we don't have any corrections for a GNSS receiver, and so the iPhone just assumes a random start point. But it's nice to see that the relative distances between the points is very accurate, giving us about 1/10 of error over 100 feet with the iPhone 15 Pro.
If you like this video, then make sure you subscribe to the YouTube channel to learn more about surveying, mapping, and geospatial technology.